Mrs. Elizabeth Adjeleian, Vice President Gubran, Dr. Hugo Paimali, Dean Newfang, distinguished guests, ladies and gentlemen. My name is Jag Humar, and I have the privilege of being your host for this evening. Thank you for being present this evening as we celebrate the legacy of Dr. John Adjeleian in a way that he would have most admired through a talk by a distinguished teacher, lecturer, and researcher. This year's lecture is special in a way because it celebrates a remarkable visionary, Leonardo da Vinci. Among the many talents and skills that da Vinci had was his intuitive insight into the complex phenomena of nature. This year, Carleton celebrates the 500th anniversary of da Vinci's birth, and there will be a series of events throughout the year dedicated to him. The Adjeleian Lecture is part of that celebration. And as our speaker, as I told you, we have a very distinguished engineer, teacher, and researcher who has explored the phenomena of turbulence, Professor Hugo Paimali. He will be formally introduced later. As I said earlier, this lecture is our way of celebrating the legacy of Dr. John Adjeleian. I had the privilege of knowing him from 1975, working with him until 2004 when he passed away. John had this rare person who combined the qualities of intellect, creativity, leadership, humility, compassion, and kindness. And he touched the hearts of many. And those of us who knew him were blessed in a way. I get the privilege of speaking about John every year. This is the 17th year that we are doing this lecture. After earning a bachelor's degree in civil engineering in 1952 from McGill and an MSc in structural engineering from MIT in 1955, John returned to Canada and set up a structural consulting firm in Ottawa. Adjeleian Allen Rubeli is the name of that firm now. It still is firmly established. The firm quickly established a reputation in the city and outside. And over the years, it has provided structural consultancy for a large number of diverse structures, some of which became recognized as outstanding examples of architectural and structural innovation. Among those were the very favorite of John Adjeleian, the Fathers of Confederation building in Charlottetown, and of course the SkyDome in Toronto, the National Aviation Museum in town. And in fact, most of the buildings on this campus was structurally designed by his firm. John joined the Department of Civil Engineering at Carleton in 1975, when I also joined. He served as the chairman of the department from 1976 until 1992 when he took retirement and was appointed Emeritus Professor. During his tenure as chair, he established the department as a center of excellence in teaching and research in the field of engineering, a view which will be shared by my colleague, Professor Yasser Hussain, the current chair of the department, and Professor Paul Van Giel, the past chair. John was a visionary with a unique quality to visualize how a structural form will work in harmony with the architecture of the building. He encouraged teamwork that brought engineers and architects together. In fact, he was that rare engineer who got along very well with the architects. That usually doesn't happen. Of the many honors that John received, he was the proudest of his honorary membership of the Honorary Association of Architects. The John Adjeleian Lecture has been established to celebrate the standard of excellence exemplified by John. And the lectures in the series highlight the outstanding achievements in professional practice, education, and research that have advanced the field of civil engineering and environmental engineering. It is our way of celebrating the professional achievements of John. It gives me great pleasure to invite the chair of the department, Professor Yasser Hussain, to welcome you on behalf of the department. Thank you.
Good evening, everyone. I know that you are here not to listen to me. We have a distinguished speaker that we are here to listen to him. So on behalf of the Department of Civil and Environmental Engineering, I would like to welcome you to our flagship event of the department. We have actually a record registration this year. I didn't really materialize yet, but I'm hoping that more people will show up and we'll have actually a record attendance of the lecture this year. Thank you very much and welcome to the event.
Thank you, Yasser. It's my pleasure to invite Professor Manuel Betts from the Architecture School to welcome the speaker and to introduce him formally. Manuel was in fact instrumental in suggesting that we hold this lecture because of his personal interest in the subject matter and the vision that he has about it. In fact, you can see one of his exhibits, or one of the exhibits of his students in the library, the Carleton Library, which is currently on display there, which deals with painting, which is inspired by the paintings, deluge paintings of Da Vinci. Manuel?
Thank you, Jag. This is indeed a pleasure. I've written a few words here. Before I begin this introduction, I'd like to thank the Adjeleian Lecture Committee and its chair, Jag, Humar, for unanimously approving both the initial proposal for the 2019 lecture nominee to be part of the Carleton Celebrates Leonardo effort, and the subsequent nomination of tonight's distinguished guest. I would also like to acknowledge the support of the chair, Professor Yasser Hassan. Professor Ugo Piomelli graduated from the Università di Napoli Federico II in 1979 with a degree in aeronautical engineering. He followed this by earning a Master of Science degree in aerospace engineering from the University of Notre Dame and a PhD in mechanical engineering from Stanford University in 1988. From 1987 to 2008, he was on the faculty of the Department of Mechanical Engineering at the University of Maryland, first as assistant, then associate, and finally a full professor. While there, he also served as associate chair and director of graduate studies from 2002 to 2007. In August of 2008, he joined the Department of Mechanical and Materials Engineering at Queen's University, where he is the Tier 1 Canada Research Chair in Turbulence, Simulation, and Modeling, and the HPCVL Sun Microsystems Chair in Computational Science and Engineering. Professor Piomelli has published over 100 refereed journal articles in the fields of turbulence and transition modeling and simulation. As of November 2018, his work has been cited over 7,700 times. And I should add, at this stage, one of those citations is where we, in the Carleton Celebrates Leonardo Committee, came across his name. This was in Fritjof Capra's 2013 book titled Learning from Leonardo, Decoding the Notebooks of a Genius. Referring to this book, Capra has stated the following, quote, Leonardo's manuscripts are full of exquisite drawings of spiraling vortices and other patterns of turbulence in water and air, which until now have never been analyzed in detail because the physics of turbulent flows is notoriously difficult. In this book, still quoting, I present an in-depth analysis of Leonardo's drawings of turbulent flows based on extensive discussions with Ugo Piomelli, who very generously helped me to analyze all of Leonardo's drawings and descriptions of turbulent flows, end quote. This is when we, in the Leonardo Committee, realized that we had found our modern turbulence expert regarding Leonardo. And he is not just down the 416 and across the 401 in Canada, but he is also Italian. In 2002, Professor Piomelli was elected Fellow of the American Physical Society. In 2004, He was elected Fellow of the Institute of Physics in the UK and Associate Fellow of the American Institute of Aeronautics and Astronautics. In 2009, he was elected Fellow of the American Society of Mechanical Engineers, and more recently, in 2015, he was elected Fellow of the Royal Society of Canada. Since that year, 2015, he is the editor-in-chief of the Journal of Turbulence. His present research includes studies of the flow in rivers and lakes, turbulent boundary layers over smooth and rough surfaces, model development for large eddy simulations, and flows in hydroelectric turbines. We are deeply honored to have such a distinguished researcher and educator with us tonight to deliver the 2019 Adjeleian Lecture, which he has titled The Good, the Bad, and the Beautiful, Leonardo's Studies of Turbulence. So please join me in welcoming to Carleton Professor Ugo Piomelli.
Thank you very much, Manuel, for the introduction, and to JAG and to the department head. And I would like to thank the organizing committee for inviting me. This is not my standard lecture. Usually I have equations, graphs, colorful pictures to support me. This one is way out of my comfort zone, I would say. I kind of like to be out of my comfort zone, but you know, it's risky for you. Okay, so this story begins in 1987 in San Francisco, when the Young Museum of Fine Arts had an exhibit of Leonardo's notebooks. At the time, I lived about 1 hour south of there, so on a Sunday I took the car and drove up to 80 and went to see what Leonardo had. Now, what are the notebooks? The notebooks are Leonardo's diary. They're his personal notes. He carried some paper and pencil along with him. He would sketch figures of people in the street. Some of them are studies of future paintings or sculptures, and some of them are observations. Many of them are scientific observations. Some are on subjects that are related to painting and some are not. So at the time, I knew about Leonardo. Of course, I'm Italian after all. And I knew of him as a painter that had done beautiful paintings, such as the Last Supper. This is Ginevra de' Benci. This is the one that he painted when he was still in Florence. And I knew him as a visionary inventor who had come up with ideas for things like a helicopter, tanks, flying machines, parachutes, and so on. What I did not know was the level of detail and the interesting things that you would find in his notebooks. And one of the first things that I noticed was the fact that he relied on experiments. He says, I will perform experiments before moving forward. And he wants first to describe the experiment and then explain it. This is 100 years before Francis Bacon, before Galilei, before Newton. At a time when the church, which was somewhat powerful in Italy, the church was not looking very positively on experimental knowledge. Aristotelic philosophy was more speculative. So I thought that that was quite interesting. Another thing that struck me is the inventiveness of the experimental methods. And the detail of the scientific observations. And one scientific observation that was particularly interesting for me was this one. He suggests adding millet seeds in water to visualize the motion of the waters, the bubbles, the vortices, and everything that's happening there. And later on, in another observation that's accompanied by a sketch of water falling out of an orifice, he says the same thing. The motion of the seeds will show you the water that moves with greater speed towards the outflow and its origin. If we want to visualize a flow, we put particles and watch how the particles move. And then we do it with smoke or with dye. But particles are particularly useful because you can also take two snapshots, look at how far a particle has moved between these two snapshots, and thus measure the velocity of the flow. So I thought, wow, this is 1500, and he has figured out flow visualization already. So I started looking for the notebooks. And I discovered what width of subject material is in the notebooks. Some of the subjects that he discussed are related to painting, optics, for example. He was interested in the perception of color, anatomy, geology. If you look at the Vergine delle Rocce, one of the paintings that I showed before, there are some very detailed rocks, obviously, as the name says, the Virgin of the Rocks, right? But what interested me, of course, being a fluid dynamicist, was hydraulics. So I started looking for hydraulics in particular, and there are a very large number of notes that have to do with water. He seemed to have been very fascinated by water. There are many observations. In fact, at some point, he plans a treatise on water. And it's in that particular page, he sketches 15 chapters and says that it will contain 730 conclusions. They are not there, perhaps fortunately. And then there are sketches of separated flows. These are what we call separated flows. I'll show them. I'll talk about it later. Flow pumps and water lifting devices, all sorts of vertical structures, and flowing pipes. I did not know at the time, well, until I looked at those, that Leonardo had such a detailed scientific interest in those things, but I was interested. And so that was, as the movie says, that was the beginning of a beautiful friendship that has resulted in a lot of things for me. For example, this is the first page of my thesis, PhD dissertation, and you see in the corner there, here, you see a quote from Leonardo that had to do with my work. And then I had some very interesting discussions with a philosopher, Virchow Capra, as mentioned above, and then, of course, I've been invited to give a prestigious seminar, so that was a very nice event. So, let's start talking a little bit more about Leonardo, and I would like to start this discussion talking about Leonardo in going back to 1482 in Milan. At the time, the ruler of Milan was Ludovico Sforza, known as Il Morro. He was not actually the Duke, he was the uncle of the Duke, and he was regent during the minority of the Duke. Eventually, he managed to get the Duke out of the way, and the Duke conveniently died at the age of 25, at which point Ludovico Il Morro became Duke himself. Now, Ludovico Sforza was aware of the fact that he was not legitimate Duke of Milan, and he wanted to legitimize his rule, and so he embarked on a public relations campaign to show how rich and cultured his court was. Milan at the time was industrially very advanced, but culturally, compared, say, with Florence, was pretty much a backwater. So he started patronizing the arts, inviting famous artists to his court, and Leonardo, who at the time was 30 years old and had started getting commissions from various churches and so on. So he had left his apprenticeship with Andrea del Verrocchio and was starting to go out on his own. However, for some reason, he was in trouble with the law. And so he decided to try to move. And in particular, he wanted to go to Milan. So he wrote a letter to the Duke explaining how good, well, let's say to introduce himself. And we have a draft of this letter in his notebooks. It's an extremely interesting letter. He itemizes the thing. You can see the numbers there in the margin. And what he says is, he means I have designs of, I suspect, light and strong bridges, siege machines, destroying fortresses, light and easy to carry mortars and bombards, warships, dig tunnels, make covered chariots, more bombards, catapults, trebuchets. And then in time of peace, he's an architect, he can build canals, can do sculptures, paint as well as any other, and he will make an equestrian statue of the father of the Duke.
My father said, you didn't brag him, you just state facts.
Well, the fact is that he had not done nothing of that sort except for the painting. It is conceivable that in Verrocchio's shop, he had seen the casting of mortars and bombards and things like that. But he certainly had never built a warship. He had never dug a tunnel. He had never seen a catapult in his life, probably. He had never designed a building or so on. So I thought that the first thing that struck me in this was the self-assurance, let's say. The second thing that struck me was the fact that he knew even then that defense funding is much easier to obtain than funding for the arts. Any of my colleagues in the humanities will tell you so. And the third thing was the curiosity. He was interested in doing all these sorts of things. He was a painter at the time. That was how he was bringing home the bacon, as they say. But he was interested in all those things. He was going to study them and find out how to do them. And this is shown in the variety of subjects that are in his notebooks. And I will, of course, since I work in turbulence, I will concentrate on two that are more closer to my area of interest. And what I plan to do for the remainder of the talk is I'll show you 4 examples of observations that you find in Leonardo's sketches, and I will try to relate them to our present knowledge of turbulence and aerodynamics, showing not only the visionary part, the good things, but also every time he was wrong, because there are a lot of times when he was actually wrong. So the first example is what we call Reynolds decomposition. There is a page in his notebooks in which he has the drawing of an old man, very beautiful drawing of an old man. And on the other side, there is a note that we'll discuss in a second. And there are 3 drawings of flow behind a semi-submerged obstacle. That's the technical name of the wake behind the post that's sitting in the water. And the one in the middle, the small one, is actually the drawing of a head of hair. That's pretty identical to one that you see in a later sketch of Leda. Now, he wrote in mirror image. First of all, he was left-handed, and he wrote left to right and also in mirror image. So you would have to put his writings in front of a mirror to read them. Unfortunately, we can just flip in software, so we can read them. And what he says there is, by the way, the standard translation of the notebooks is by Richter. And that's a very beautiful translation. It's very poetic. Unfortunately, Richter doesn't know science. So all the translations that I'll show here are my own translations. So what he says there is, observe the motion of the water surface, which resembles that of hair, that has 2 motions, one due to the weight of the shaft and the other to the shape of the curls. Thus, water has eddying motions, one part of which is due to the principal current, the other to the random and reverse motions. Now, that's exactly the way we look at turbulence. Here you see the main current, and you see here all these, we call them eddies. And you see that there is a lot of them. They're somewhat random. You cannot predict when they will happen, but they're important. And they're important because you find them in all sorts of turbulent flows. This is the visualization of the flow in the combustion chamber of a jet engine. And you see these whirling motions here too, right here, for example. Now, those eddying motions are important because they are responsible for the transport of mass, momentum, and energy. Basically, they play the role that your spoon plays when you're mixing sugar, milk, and coffee. They mix everything up, and they are responsible for dispersion of pollutants, for cooling, for aerodynamic drag. Now, their motions are not random, but they appear randomly. So that's what makes their prediction so difficult, the random part. However, if you are working in turbulence, you have to know how they behave. Otherwise, you will not be able to predict anything about a turbulent flow. Now, it's pretty hard to predict random events, and it's particularly hard to do it when you're looking with things of scales that are so different as the eruption of a volcano, or the flow in a wind farm, or the behavior of the flow on the wings of an airplane, or this is a calculation that one of my students did, the cloud of dust that's lifted up by a hovering helicopter, the flow in a heart valve, the flow in an airplane. All these are turbulent flows, and we need to study them, and they're all turbulent. And they have eddies. So what do we do? Well, we go back to the same idea that Leonardo came up with in 1506, I think. 1506, 1507, this was written when he was in France already, in Amboise. What he proposes, what he observes, the distinction between main flow and the eddying motion was actually mathematically formulated by Osborne Reynolds at the end of the 19th century, and we call it the Reynolds Decomposition. And we use it, actually. You'll be tested on these equations later. What we do is we write the velocity here as the sum of a mean contribution and a fluctuating contribution. And the mean is what Leonardo would call the principal current. And the fluctuation is what he would call the random motions. So not only we take this, the idea of the decomposition in the mean and random part, but we actually write equations. And we have a set of equations known as the Reynolds averaged equations, in which you obtain the velocity of the principal current, and all the random motions are in this last term. Now, if you can solve this equation, you get everything you need to know about a turbulent flow. So the fundamental approach to study turbulence is based on this decomposition, and is based on this decomposition that Leonardo foresaw 350 years before it was put in mathematical form. Now, how do we solve this equation? Well, there are two ways to do so. One is the engineering approach. The engineering models, if you're interested in a problem for engineering applications, you're not interested in the detail. You want to know the global picture. So what you're interested in is only the principal current. You don't want to know what happens to the various random and reverse motion. And you just want to know their global effect. So you obtain a very broad picture, very broad paintbrush. But it's very useful if you're looking at large problems. This, for example, this is the flow in a hydroelectric turbine. The water is coming down along that spiral tube and goes into the turbine, and the turbine revolves and generates electricity. And this type of flows are studied using those equations and looking only at the motion of the principal current. The other approach is a more detailed physical approach in which you look at each single eddy and you try to predict how these single eddies will affect the flow. And when you do that, you get a very, very detailed picture. This is a simulation that one of my students did, and it's basically water flowing on top of a sheet of sandpaper. You can see the grains of sand. And the little dots are simulated millet seeds. You can solve them in a computer, and you can put computer models of millet seeds, and you see how they move. And you see in this particular case, what's interesting is that while the millet seeds are inside, between the sand grains, they move upwards, backwards, forwards to the side, and then eventually they get picked up by the main current, and then they start moving around. This is probably quite obvious, but everything is obvious after you've seen it the first time. And it's actually very important from the point of view of the engineers to know what's happening. In fact, my job in life is to look at the detailed models, study the detailed models like I showed before, but use them to try to devise better models for the engineers. So this was the first example how Leonardo saw this decomposition so many years ahead of time. The second example I wanted to show is the study of separated flows. In aerodynamics, we try to have streamlined body, we call them. In a streamlined body, the fluid, air, water, whatever it is, not ketchup doesn't work, air, water, glycerin, follows the shape of the body. Now, if you put this body at an angle, the flow doesn't follow the shape of the body anymore. And in fact, you see that there is a region behind the body where there is pretty much dead air. There is very little motion. Some motion is upstream, not downstream. And there is a lot of turbulence, of chaotic motion at the edge of it. This phenomenon is called separation. And separation is very important. It causes drag, it causes loss of lift, airplanes crash if you have separation. And it's been very important for the development of aerodynamics. The Wright brothers had an idea of what separation was, but not a very good one. Before the Wright brothers, there was no understanding whatsoever. In fact, there were some very famous people who came up with incorrect hypotheses about separation. And the first real understanding of the physics of separation comes in 1904 in a paper by Ludwig Prandtl, 1904. What did Leonardo do about that? Well, he observed. And there are a lot of sketches in his notebooks of separated flows, either for immersed bodies, for partially immersed bodies like this one. And this is a particularly good one that I would like to focus on. Here you see you have a plate that's sitting at an angle to the flow, and you see a number of interesting things. First here, there is this rope-like structures upstream. This is called the horseshoe vortex. And it's a vortex, so the fact that it looks like a rope that's twirling is actually the way it is. However, there is only one of them. He has two. And also he has two rotating in the same direction. You cannot have that. If you had two of them, they would have to rotate in opposite direction. But he saw those vortices, and then also he sees there is a depression here behind the object, and there is a region of turbulent flow that's coming up from that depression. Okay, this is a movie of a similar situation. There is a plate that's immersed right now in the water, and it's carried out very fast. This whole movie takes 0.47 seconds in real life. And you see what's happening, and you see the vortices here, you see the depression, and you see the turbulent motion that's coming from underneath the plate. So you can see all the ingredients that are in Leonardo's sketches. Okay, this is another drawing. These are so-called bluff body wakes. We call them bluff body wakes. You see there is cylinder that's, and the flow is going from left to right. And behind the cylinder, Leonardo sees these couple pairs of vortices. He sees several of them. You see here there are two, perhaps three. In reality, there is only one pair. Also, these lines, he recognizes that the flow is attached in front and separates in the rear. But these lines are not streamlines. That's not the way the millet seeds would flow. These are more like the shape of the free surface. You would see the free surface. Now, what's quite interesting here is the fact that on the right, you see the mean flow, and you see these two vortices behind in the wake of the cylinder. In reality, that's not the way things work. In reality, you have one vortex being shed on the bottom and then one on the top, and they alternate between top and bottom. So you see this is an instantaneous picture, and you see that there is one on the bottom, one coming from the top, one coming from the bottom, and one coming from the top. Now, what's interesting is that Leonardo also had this in his sketches. He had an asymmetric shedding, we would call it. So now, the question arises, were the top sketches completely wrong, or was he already seeing the mean flow? So are these incorrect sketches or realistic sketches, or are they abstractions? Conceptual ideas of what the flow will look like on the average, even if instantaneously at any time, it doesn't look like that. At any time, it has a vortex on the bottom and a vortex on the top. But if you look at the average flow, it will have a symmetric pair. There is a lot of, I don't like to get into the head of people who write things, but there is a lot of scholars that believe that those were actually conceptual sketches of the mean flow. Again, some things are wrong. He has a series of vortices in the wake instead of only one pair, but something is right. Also, if you look at this sketch on the bottom here, you see here he has one vortex on the top and one vortex on the bottom, and that's exactly what we see here. There is a rotating motion this way on the top and this way on the bottom, and the dead air in between is caught between these two vortices that are formed at the edges and are drawn. Again, this one is not just a conceptual sketch. This is actually a flow visualization of an instantaneous flow, I think. The next example is the energy cascade. Energy cascade is what we physicists and engineers use to describe the exchange of energy in a turbulent flow. And Leonardo had a number of sketches like the ones in the announcement for the seminar, of water falling on water, he calls them. Again, those are from his last years. Those drawings are from his years in France. And what do you see here? You see the water falling and forming a number of swirling motions, the eddies, the random and reverse motions, as he would have called them. And there are some that are bigger. Here you see there are bigger ones that are drawn in darker color shades, and there are smaller ones, and eventually they disappear. And if you look at one of them in particular, he says things like, first of all, he notices that the large eddies, there are not very many, and there are a lot of small ones. And then the large eddies have a lot more energy than the small ones. The large energy carry larger objects, the small one carry smaller objects. Again, this may appear as an obvious observation, but it's tremendously profound because it took about 400 years before we came up with the same picture of turbulence. That's called the energy cascade, and it was initially proposed by Richardson in 1922. You see, it's right here. You see the main motion, and then you see all these eddying motions. And in a flow like this, the largest of those eddying motions, The largest of those eddies are about 10 meters. The smallest ones are 1 millimeter or less. So there is some big ones that you can see and a lot of small ones that you can see and a lot of small ones that you cannot even see. And it is true that the biggest one have more energy. And in fact, the picture of the energy cascade, as we call it, which was first proposed by Richardson in 22 and put in a mathematical form by Kolmogorov in 1941, is exactly that. That energy is, the large eddies have a lot of energy and then they break up and form smaller eddies. And since one eddy breaks up, there is two big ones, one big one and two small ones. But then each of the small ones breaks up again. So there will be 4 of the even smaller ones. And since they start with the same amount of energy, but they're dividing it into 4, the small ones have a lot less energy than the original one. And then there is smaller one and smaller ones until eventually they are so small that they get dissipated by friction. Now, the whole idea of this energy cascade, what's really important about it is the fact that the amount of energy that's at the top of the waterfall, the big eddy, is just transmitted down to lower and lower levels, but it's the top of the waterfall that determines how much energy there is. So it's the largest eddy that determines how much energy there is, and it just transmits it to smaller and smaller and smaller eddies. And pretty much all of turbulence theory and anything that is used in fluid dynamics to predict turbulent flows, the airplanes you fly on are designed using this theory. So it's a pretty important one. The fourth example and last one is aerodynamics. The first thing that he noticed is the importance of relative motion. So the motion of the objects against the air at rest is the same as the motion of the air against an object at rest. That's what we do when we do wind tunnel testing. We don't have the airplane flying in the air. We have the air flying over the airplane. Now, this concept is pretty obvious, again, after the fact, but it was not obvious at all at the time. And in fact, the first actual experimental proof of this was carried out by Gustave Eiffel in 1910, 1917, something like that. Gustave Eiffel is the guy who designed the Tour Eiffel. And at the end of his life, he decided to become an aerodynamicist because he also had trouble with the law. So he had abandoned his job as a structural engineer. And he gave tremendous contributions to aerodynamics. In particular, he started by dropping objects off of the first level of the tower and measuring how long it took them to get to the ground and to determine the forces. Then he built a wind tunnel, and that wind tunnel is actually the prototype of all wind tunnels that are used in every single university and research lab in the world. Those are called the Eiffel tunnels. And by looking at the results of the experiments in the wind tunnel and the drop test, he came to the conclusion that, yes, they are the same. You can run a wind tunnel and get information and use it for to build airplanes, let's say. So again, this is an idea that Galileo had the same idea. About 100 years later, in the Dialogo sui massimi sistemi, he talks about this, and but he does that in a different framework. He talks about it because he's interested in proving that the Earth can move around the sun, and we do not feel the motion. Leonardo is more fluid dynamics oriented. Then he wrote a treatise on bird flight. Now, at the time, the understanding was that birds are floating on air. Leonardo's initial hypothesis was different. He thought that by flapping the wings up and down, the birds create a high pressure on the back. They compress the air below the wings, and they're supported by the compression of the air, by the high pressure on the bottom side of the air. Now, that's not the way things work. If you look at an airplane, for example, the airplane is not supported from the bottom by high pressure. It's lifted from the top. The top surface provides most of the lift. Now, later on, however, Leonardo revisited his theory. And there is a long paragraph in which he talks about the thinness of the air above the wing. The thinness of the air above the wing is the low pressure. That's what that's how actually wings of airplanes or birds and so on work. He also recognized that the birds don't flap their wings up and down. The motion of the wing beat is more like breaststroke, like this, forward and backward. What the wing beat does is not support the bird. It propels the bird forward. And then once the bird is moving forward, the lift is generated by the flow of air over the wing, just like a normal airplane. So the flapping of the wing is doing nothing but what the engine of a turbojet would do. So I think this is another example of how his eye, the eye of a painter in a sense, was capable of very detailed observations and how he was able to abstract the fundamental ideas from these observations. Okay, so let's start summarizing. I think there are several very good things that come out of his sketches. First of all, his intellectual curiosity. He was interested in a number of different subjects, and he studied them, and he made notes, observations, drawing, and so on. Also, he recognized the importance of experiments, which at the time was a very big step forward. The power of observation, the detail with which he observed phenomena that occurred very quickly, and how he could abstract the ideas is also quite unique. The willingness to go beyond the accepted knowledge, the relative motion, the importance of experiments, those are all trademarks of a good scientist, I think. And also, very important, the willingness to change his mind. So many of us suffer from the lack of this particular feature, unfortunately. And I count myself among those. I do change my mind every once in a while, but I have to be hit on the head with a very heavy hammer before I do that. The main problem with Leonardo's work is that he did not publish. He wouldn't have gotten tenure at a modern university. He wrote his notes and he kept them for himself. In fact, he wrote them in a very cryptic way, written the other way around. He didn't want people to know about them. Well, of course, some of his observations are completely wrong. The helicopter, for example, would not work because the helicopter is designed as a screw, and the screw is pushing on the bottom side in this case. And the lift doesn't work like this. First of all, for the lift, you need the trailing edge, and there is no trailing edge here. And second, you need to generate low pressure on the top, and this would not do that. That's not a big flaw, in a sense. He did not have the measurement techniques that we have now, and he did not have the mathematical language. Those are difficult problems, and you cannot really solve them by looking at them. You can make some very useful and important observations, but if you want to know how an airplane flies, you need equations. You need equations, and you need to be able to solve them, or you need measurements techniques, you need experiments, and he did not have that. He did recognize the importance of mathematics, but at this time, there were only two types of mathematics. There was algebra and there was geometry. He saw that the geometry was more suitable because geometry deals with continuum variables, like differential calculus, which is what we use now. Whereas algebra, arithmetic in particular, is what he was thinking, deals with integers. So he tried to develop geometria fatta col moto, geometry of motion, he called it, which is some sort of topology. He transformed one shape into another and tried to calculate the properties and so on, but he didn't get very far from that. And the other problem is that he was not very systematic. He would start being interested in one topic and then sooner or later lose interest and start working on another topic. So when he says that he will write a treatise on waters, but he never did. So his notes are completely disjointed, and a lot of people have been writing PhD dissertation trying to put them in order. What's beautiful are, I think, first his detailed sketches. the fact that with these sketches, he manages to conceptualize very complex theories, and most of the time, they're correct. Sometimes he's wrong, but surprising is the number of times in which he's right. Also, if you read his explanations, I think the sketches are much better than the explanations, much clearer in most cases. So, at the end of the day, what do I get out of my studies? Well, there is a lot of admiration, of course. There is admiration for the details. There is admiration for the ability to abstract complex concept. And there is admiration for the fact that he draws such beautiful old men and such beautiful young women and children. There is also a lot of regret, because the only thing that he left actually are the paintings. The notebooks were never formalized. He never wrote them up. He never published. So nobody knew what Leonardo had thought. How far would Galileo have gone if he had known about Leonardo's observations on relative motion? Would we have been able to fly earlier if we had started our study of separation based on Leonardo's observations instead of starting from nothing? Newton used to say that, wrote, I think, that I've seen further because I stood on the shoulders of giants. Well, the unfortunate fact is that Leonardo was a giant who didn't want anybody to stand on his shoulders. And that's a pity, and leaves a little bit of sadness at the end. But then again, I like to play the blues, so if a story doesn't end sadly, I'm not really that happy. Thank you very much.
We're going to have a question period. Anybody have a question? There's one. There's a microphone right at the end.
What time and how were Leonardo's notebooks discovered?
Sorry?
What time and how were Leonardo's notebooks discovered, if you will?
What time are which discoveries? The follow-ups?
Follow-up.
Well, as I said, separation is 1904. The real understanding is 1904. The Reynolds decomposition is 1880s. So we're talking 300 and something years later. Now, of course, Osborne Reynolds had math, knew math. Prandtl knew math, had the tools at his disposal. So he could describe separation based on partial differential equations, and Leonardo could not do that. So Leonardo could only observe. Reynolds and Prandtl could actually explain. But that was not Leonardo's fault, right?
We have one right here.
What motivated the people who were looking at Leonardo's work, particularly the first people to pick up on it?
That's a good question, and I'm not quite sure I know the answer. I think a lot of his notebooks were lost because they were sold, broken apart and sold. In fact, that's why we have so many collections, Codex Leicester, Codex Atlanticus, Codex this, and manuscript A, B, C, D, E, and so on. And they've ended up in the hands of all sorts of people who would buy them because they were Leonardo's, because they were drawings. Windsor has a collection of drawings. Every once in a while they go on exhibit, but it has a gigantic collection. So I think it was, I think that his work has been analyzed in a more scholarly fashion starting probably around the beginning of the 1900s or so. But it was, I think there was some of it was bought by the Duke of Leicester. What does the Duke of Leicester? There is a Leonardo painting that belongs to the Duke of Buccleuch. He's the richest man in Scotland. And he owns a Leonardo painting. It's scary.
Anybody else? Oh, right here.
Professor, I've always wanted to meet an expert in aeronautics. It always puzzled me the difference between a fixed-wing aircraft shedding vortices, the horseshoe vortex, and what happens to this vortex with a flapping bird.
That's a good question. Well, a flapping bird is not flapping actually up and down. A flapping bird is moving, is doing breaststroke. Well, the vortex is still there. You cannot generate lift if you don't have vortices.
Is it a horseshoe vortex or is it something else?
It depends on the wing also. You know, if it's a sparrow, the wing of a sparrow is very different from the wing of an albatross, right? And the technique that the sparrow uses is very different from the technique that the albatross or the turkey vulture uses to fly. So the shorter the wing, the more if you want a technical explanation, the shorter the wing, the more the lift is generated by the vortices. In a delta wing, lift is generated by completely different mechanism than in a regular wing. You don't have the horseshoe vortex, you have leading edge vortices. So if you want me to get technical, I can do that. But the main thing is that the shorter, the lower the aspect ratio of the wing, so short and stubby, as opposed to long and thin and long, the more the lift mechanism is different from the lift mechanism of a general airplane. Bumblebees. Bumblebees generate lift by vortices only, not by the vortices that are shed by the beating, not by the standard mechanisms of the regular wing. But we can talk about that perhaps.
Certain birds, when they flap, they rise when they're flapping, and then descend when they're coasting, and others it's the reverse of that, or are they all consistent?
Well, when you are not moving the wings, then you are not generating more lift. So in order to go up, you have to get into an ascending current, thermal. Otherwise, you will glide down at an angle that depends on the elongation of the wings. The glide angle is very strongly dependent. The lower to get a low glide angle, you have to have very elongated wings. So all birds, if they're left alone, will glide down. Only way they have to go up is either by propelling themselves or by sitting in a current of air that's moving upwards. That's what vultures do. You see them circling.
Hi. We see that Leonardo's handwriting is left to right.
Mostly.
Right to left, excuse me, inverted.
Yeah, mostly. Sometimes he writes normally. The letter he wrote to the Duke of Milan was written normally.
So it's intentional. So my question is, do we see that inversion in any of his work, in his drawings, in his perceptions? Does he skew things invertedly in that way?
As I said, I don't like to get into the head of people. So I'm not quite sure. But it's certainly a very legitimate point that you are making, undoubtedly.
I think we might have time for one more. Well, we have a couple here.
Not necessarily a question, but I am curious to know how long would take Leonardo da Vinci, if he was here today, to figure us out? Would it be days, weeks, months?
Well, it's an interesting question that you ask. And there is an Italian movie with Roberto Benigni, you know Roberto Benigni, one who does Life is Beautiful, in which he and the other character, another Neapolitan comedian, are carried out back in Leonardo da Vinci's time, and they meet with him. And at some point, they start talking to him, and one thing is that he cannot learn how to play cards, the simplest game of cards, but they describe the train to him, and then they go their own way. And the last scene of the movie has a train coming and Leonardo da Vinci getting off the train. So let us say that at least the Italian screenwriters think that he would have caught up very quickly.
I think the last one was there.
We can maybe take more questions.
I don't really need a microphone. I can use my theatrical
Oh my God.
professor's voice. I have 35 years of notebooks worth of derivations and very beautiful kinematic geometry diagrams, and even notes on the performance of the Montreal Canadiens in the playoffs. Yet nobody is certainly ever going to be interested in my notebooks other than myself. How was it that these notebooks were identified as scientifically valuable back in the day, back in the 16th
Well,
century?
they weren't identified as scientifically valid. In fact, they were lost. He left them to one of his pupils. And at his death, they got completely lost, and nobody looked at them. They have been identified now. So now there has been, recent years, there has been an analysis of the notebooks. In fact, there is an interesting initiative. The Museo Leonardiano in Vinci, the town where he was born, has digitized every single page of his notebooks, and it has the text in Italian, of course, but it has the text, and you can do searches by words. So if you want to know millet seeds, you look miglio, and you look up and you find all the pages in which he mentions millet seeds. It's an amazing tool, but it's recent. You know, in 1600, nobody knew about them. He was a celebrated artist, of course, but not as celebrated as others because he did not complete his work. Even the people who gave him commissions knew that he was not very good at completing his work. So usually they forced him to take helpers, hoping that that would get him to do the job. But you know, how many famous paintings of yours are in a museum? Okay, that's a problem, I think. Once you get 13 or 14 in a museum, I think your notebooks are going to start becoming very... Also, you've got to die first. Sorry about that. Usually it works better, posthumously.
Okay. I'd like to call Yasser Hassan for some presentations to the speaker.
Thank you very much for the interesting speech. So these are just small memorabilia to remember us. I'm just going to get this piece. So this is
Oh, thank you.
to remember John Adjeleian Lecture.
Thank you.
Thank you very much. You can put it back.
Yes.
This is just
Oh,
at Carleton
wow.
University.
That was a very fast turnaround, I have to say. Thank you. Thank you very much.
Thank you very much. Thank you.
Thank you, ladies and gentlemen. Thank you, Dr. Ugo Paimelli, for accepting our invitation to deliver the 2019 John Adjeleian Lecture. It has been a wonderful experience for us. Thank you for sharing some of your remarkable work and by illustrating what 500 years ago Leonardo da Vinci had the insight to understand and appreciate some of these complex phenomena of nature. Now, it has been our tradition to use this time to recognize those of our students who have excelled in their studies. So I'll request Vice President Gubran, our Vice President for Research and International, to join us here, and Professor Siva Thelan, my colleague, to present the students.
Good evening, everyone. It's my pleasure to get this going. We have a list of award winners. Some of those students are here, others are not around. So I'd like to I'm thankful for Professor Gubran for assisting me with this. Our first award is for John Adjeleian Scholarship. For this one, I'd like to invite Mrs. Elizabeth Adjeleian to join us, please. invite Ms. Nantini Porchelvam, the recipient of the John Adjeleian Graduate Scholarship. So you can start with Nantini. Maybe you can turn around for a photo with the dean. And okay, come in. Can you? Okay. We have a second winner, Ali Abdul Hamid, who is not present here today. Okay, thank you, Mr. Adjeleian. You can go and take a seat now. Our next award is Professor Jack Morgan Humer Graduate Fellowship. I'll please invite Jack to join us the stage. And the winner of this award this year is Prasanna Rousseau. Prasanna, please. Our next award is Professor Ata Khan Graduate Scholarship. I'll please invite Professor Khan to join us. And the winner of this award is Shahriar Mohammadi. Please join us here. Thank you, Professor Khan. Thank you. Okay, thanks. The other awards will be presented by our Vice President, Research and International, Dr. Gubran. Next, we have the Koshar Family Scholarship Award winners. First, Dawal Amlani. Then Srinivasan Hari Ramsubbu. Srinivasan is not here. Okay, thank you. Sorry. Then Amitesh Malhotra. Now we have NSERC postgraduate scholarship winner, Tarek Abimura. And then we have Ontario graduate scholarship winners. Of the 6 awardees, we have 3 of them here with us. First, Yakmur Babaglu. Then Syed Sahid. Then we have Robbie Venus. We also award excellence in teaching assistantship awards both at the departmental and the university levels. At the departmental level, we have Seung-Yeon Hong. And we have Brody Hobson. And at the university level, we have an award this year, Ahmad Hassan. Thank you. At this time, I'd like to invite all of our award winners and the Dean Matthias Newfang and Dean Fred Afar and Professor Yasid Hassan, our chair, to join us for a photograph with the students. And I'd also like to invite Professor Jack Humar to join us as well, please. And our speaker, Professor Hugo Piomoli, please. Maybe we can.
I think you should be right in the middle.
Yeah.
This is about students. Students should be showcased.
As we near the conclusion, I would like to take this opportunity to express our thanks to all those who worked tirelessly to make this event a success. They include members of the organizing committee who worked with me, Professor Manuel Bertz, who first suggested the idea of relating this year's lecture to the celebration of the 500 years of Leonardo da Vinci and his intuitive understanding of turbulence, Professor Siva Sivathalan and Professor Ehab Zalok. Special thanks to Ms. Alexandra Leroux and Laura Kilpatrick, event administrators for the faculty, and to Ms. Kay Kesselman, the departmental secretary, all of whom devoted many hours to organization of this event, and whose contributions are largely responsible for the success. I'll also like to acknowledge the great support of the departmental chair, Professor Yasser Hussain, and of course our thanks to the speaker, Professor Hugo Piomoli. Ladies and gentlemen, please join us in the adjoining room for a reception. Thank you very much.